Hey guys, how's everything going? This is Jason. I published my 20th video of React source code walkthrough, number 20 last week, but I realized that number 19 is missed out. I somehow forgot to record this episode, so I'm making this one now. This episode is about key. Every time we render a list, React actually forces us to not forces, but warns us to provide a unique key property to somehow improve the performance. It's addressed on the homepage, so if you read it carefully, you will notice that it is not something that you can how should I put it? You should depend on to say, okay, if the key is the same, then there will be no rendering happen. It's not for that actually. It's the key is some internal performance improvement to avoid recreating the fiber node. That's it. We will go through how it works, so no worries. When we were in the list, it's actually the list should be some children of a parent, right? So the secret lies into reconcile children array. Me myself is a little bit familiar with that, so I'm just jump straight to it. You can dig into some details by yourself. There's a long paragraph of explaining the algorithms there. It says this algorithm cannot optimize by searching from both ends since we don't backpoint of fibers, blah blah blah. Anyway, so one thing we should notice that the React, as we've already covered in the previous video, React actually treats the tree, even if it's a tree structure, it will treat all the nodes in one order, right? So it's like a linked list. It's the same for the children. It's not an array. Because of that, like if you think of a linked list, you'd only know what's your child next node is, right? You don't know the index. You cannot access the last one instantly. So it says React doesn't do two-ended optimization because we don't have backpointers on the fibers. Yeah, reasonable. I'm not sure what two-ended optimizations is. We will have some guess right away. Don't worry. So suppose we have an array like 1 to 10. If some items change, like position 5 is changed, then there might be a lot of possibilities, right? So how we can make that change? Like if if number 5 is inserted, or it's swapped by some other elements at some other index, or if somebody's like this item is shifted and then some items insert at the same place. So we cannot know what exactly triggers this change, and by that we mean we might not be able to find the most optimal approach of diffing. For example, if we have a result array like this, it's random like this, right? We don't know what it is. How should we transform it with the minimum cost? The cost has two parts. One is about the algorithm itself, like cost of analyzing. So what might be the optimal approach? But there's another cost of if we do that approach, we need to transform the array, right? The cost. So if we are talking about DOM node, the movement, the recreation of nodes all cost time. So the total cost, personally, it constitutes two parts. For an extreme example, if we have this like totally reversed array, it might be cost a lot of time to find the optimal approach, like how we can do the different, right? But if we reversed it into like for the original array, it's 10 to 1. Now we reverse it. We don't reverse it like this. Wait a minute. Oh yeah, I'm sorry. About two-ended optimization is like if the initial array is like this, and somehow the array of the result is something like this. But if we, it's complex. But if we reverse them both, you will see that it's easier for us, right? Because the first 4 elements are the same, so we only needed to tackle the rest part. What I want to mean is that React takes an compromising approach without trying its best to do the optimization about analyzing part. But yeah, heuristically, just do some easy approach, not do some fancy stuff. It's already documented in the source code, so if you're interested, please take a look. So what is actually our React's approach? We've already see that if we take a look at this example, I think most of the time the order should be kept, right? Basically, there should be not many changes. So React goes to keep track of cursor of the original array, the result array, and compare them. If they're the same, then we both move on. It's like a two cursor algorithm for the algorithm problems. I believe you're already familiar with that. So once they meet something different, they just stop. Okay, so we stop there, and so we don't. It's like here the same. Okay, and then we met 5 and 12. It's not the same, so we stop there and try to fall back to some other approaches. For the other approach, one of the approaches is that, okay, because if we already compare that they're not the same here, we could recreate all the fiber nodes from here, right? Yeah, basically for the worst part, we could just recreate everything from the zero, from the start. It's not optimized, so we compare, reuse the fibers what we can use to the maximum, and then if we made something different, we would try to search for the rest fiber nodes to see if some fiber nodes we can use. For here, like we go to 12 is different than 5, so we say, okay, the rest we can use the fiber we can use is 5, 4, 3, 2, 1. Now we met 12. Is 12 in them? No. And then, okay, recreate new one for 12. And if it is, go to 11. So 11 is in 5, 4, 3, 2, 1? No. So we recreated 11. And if 3 is there, you say, if 3 is there, yes. And then we reuse that fiber and mark it as move because the position changes. And then just to go on. At last, every node that is not used will be removed. And the final fiber, the array, not the array, linked list is reconstructed. So you see that the algorithm here, the key is actually to mark that what the actually in fiber you are, that we could reuse you despite where you are. Yeah, the algorithm here is like we first the React actually keeps a set map key to the fiber, and it's like and the searching part is constant time complexity, but the space will cost like linear space complexity. So it's not very fancy. It's very simple. Let's just go straight to the source code. It's been long. I've added some comments here, so let's go through them one by one. As I've already said, it's like two-pointer cursor algorithm. This auto fiber is the cursor for the original fiber list, and the index is the new element. Remember that the children is elements and fiber is a fiber list. We are comparing them and then try to create a new fiber to replace the old fiber. So yeah, this is just a normal for loop, nothing fancy. But there's a if here is a bit mysterious. It cost me some time to understand what is happening, but I've already created a post about this. That's because the index on the fiber is the index of the original element. It's not the fiber itself. What it does mean is that we already know that React actually ignores the empty values, right? Like the Boolean, like the null, like the undefined. So for the final linked list, there might be 3 items. There might be 3 fibers in all, but the original element, there might be more than that, right? Like 5 of them, but 2 of them are empty values. But the index is not the index of the fibers, it's the original element. That's why if you made some cases like old fiber index is bigger than new index, it means that there are some empty stuff. There are some empty stuff in the original element, previous element. So you are comparing to them. So for that case, we say, okay, we're comparing to empty. That means we set the old fiber to now, and next old fiber, it's still the old fiber. You see, that's it. Yeah, please visit my previous post about it, about empty values. Yeah. Okay. Now, and we compare them. This update slot will compare in the fiber and to see if if they are the same component type, then we just do the update reconciliation. If it is not, we just ditch the old fiber but create a new one, right? This is just a simple diff for a single node. So we create a new fiber. It might be now. If it is now, we need to. Oh, wait a minute. Okay, if it is now, it means that we cannot update. Yeah, it says here, update slot. We cannot update. It will return a new now. So it says we need to create a new one, right? So we break here. And there's some other stuff. So if we manage to update, then the old fiber, blah blah blah. If old fiber, now we have a new fiber, and wait a minute. Why? Okay. If new fiber is now, we need to obviously either find its original position or create a new one, right? So break here. Update. Okay, now we compare the old and new. Hopefully we could match open the function update slot. We can see that if the neuter is empty, key doesn't match. Yeah, the new fiber itself might be empty, or its key doesn't match the new fiber. Oh yeah, the update slot says if the key doesn't match, then the new fiber is now. Okay, so if the fiber is now, we need to create a new one. Yeah, and that's true. So we break. If it is not now, it means that the key is the same. So we managed to do the update. And so what is here? So there's some flags to track side effects. This is just the internal optimization for initial rendering or re-render. Now we have new fiber. If it is the same alpha fiber, they should be connected with alternate. Oh yeah. If not, meaning, oh yeah, it checks. If they are not matched, they will delete the old fiber. Yep. Yeah. Okay. This one is very interesting. I'll cover it later. Here, when we manage to get the new fiber, we need to place it, right? We need to put it into the final fiber list. So this is basically what it does. It places the child, but inside of it, it actually sets the flags of this fiber to do some extra stuff. We'll soon get over it. Okay, and then we chain them up. This is a variable, keep track of the previous one, and then we connect them by the sibling. Okay. Okay, let's continue. So when we reach the end, it says new index is the end, right? We will delete all the remaining children, yeah, because they're not used. And we return the resulting first child, because in reconciliation, we need to, you can think of like a recursion. After we diff to the children array, we need to go deeper to each child, right? So we return the first child to continue the work. And then if the older fiber is null, what we do, you can see as I explained, it will, here, new fiber, create child, blah, blah, blah. Yeah, this is create, return fiber. Wait a minute. If old fiber is now, if old fiber is now, we need to create. So it says we create this fiber and then place it. Yeah, this is the same stuff. When old fiber is now, it means the old fiber list is empty. Yeah, we don't have any more existing children. We just create list for the new element. Yeah. And then last piece puzzle is, if old fiber is not now, it means that we still have some existing children, and also we have some existing new children, right? So as I said, it will create a map for all the resting fiber, and then for each of the new rest children, it will try to fetch it through from the map by the key. Yep. Wait a minute. Yeah. Existing children, return fiber, new index, or maybe index. Oh, I think the key is in somewhere. Anyway, if we don't find them, we should create one, right? If we don't find the fiber from the map, existing place the new fiber. Oh no, if we find them, yeah, if we find them, we will place them into the list, and also do the same as before, delete the old one if it is not, and then yeah, that's it. Create fiber. I think the creation actually is in this update from map. Also in update slot, it will create that inside of the function. Here is to determine if it is newly created or just to reuse the old one. Same goes for update from map. If we manage to create one or reuse one, we will do some deletion for the previous fiber and connect them up. So that's it. That's for the diffing problem. One thing I've left is the place child, as we said. It's a bit confusing here. Let's just draw a diagram and to see what is happening. So suppose we have a 1, 2, 3, 4, 5, 6. This is the original array, and we have 1, 6, 2, 5, 4, 3. This is a new linked list. Think of them like a linked list. So we can see that for each item, we have a new position. For 1, it doesn't change. For 2, it moves forward, right? The position moves forward. For 3, it moves forward. For 4, it moves forward. For 5, it moves backward, right? Originally it's 4, now it's 3. And 6 is the same. It's moved backward. So the algorithm we've covered is that if we compare the 1, 1, there's nothing to change. So we go to 6, 2, right? So now for 6, this is a new element. It's different here. So we put all of this into a map, and then search for 6 with constant time. We found it. So okay, we can reuse this fiber, right? So here's the thing. React treats this like, okay, anyway, because all the fibers that is not will be deleted. Like if 2, 3, 4, 5, if they're not reused, they will be deleted anyway. So the 6 here actually will be automatically connected to 1 if there's a DOM, right? So this is a tricky part. 6. So if 6 is moving backward, then the position, we don't need to do anything because we just wait for 2, 3, 4, 5 to go, and 6 will be placed into the right position. That's why we need to keep track of like, okay, the valid index, that's called last place index. We keep the index of like 6 here, and then 6, yeah, as I said, because 6 is bigger, 6 is moving backward, we don't need to do them, we go to 2 again. For 2, it is moving forward, right? For 2, it is the original index is smaller than 6. Yeah, what does it mean? It doesn't mean that you need to move, right? So for 2, if it is found the fiber, and then the index is smaller than 6, 0, 1, 2, 3, 4, 5 here, then it should be marked as move. And for 5, again, it's 5 smaller than 6 on the left, and then you mark as move. 4 marked as move. 3 marks as move. So in the end, what we see is that the actual move for DOM is that for 2, it will move to here. 3, 5 moved here. 4 moved to here. 3 moved here. The 6, it doesn't move. 1 doesn't move. So this is what it does. So this is the last place index. How did it works? Suppose we have like for like another one like 7. Okay. For 2 here, we have a 7 here, and then 7 is somewhere after 6, then we go to 7, and 7, the old index is bigger than 6, then we will update this last place index to 7. So if there's some elements between 6 and 7, now they should be also marked as movement if they are reused. So yeah, I suggest you take a further look at this diagram and help you understand how React do the algorithm stuff. So that's it. This is the whole diffing algorithms. It's not completely complex, and to be honest, there's a lot of to do in the source code. So the React team is not doing. I don't know. Maybe are thinking, but maybe they're not. So it's not the best, I would say, but yeah, it works. This is something I mentioned that for React, it's not for totally care about the performance, as we already know. It's that Vue.js may just says they have better performance and some other frameworks have their better performance. React actually cares about the user perceived performance, like the responsiveness and I don't know, developer experiences make the coding easier stuff. Yeah, so there's some off topic of our episode here. Anyway, for diffing, that's it. The most important part is about, I think it's here. One, about optimistic matching for the unchanged one, and then use a map to try to find the reusable fibers, which needs key to be set. That's it. Okay, so next time if you're asked what does key do in React and rendering, you could say that actually key is some hint to allow React to reuse the fiber in the list diffing. Wow, that's totally cool, right? that's so yeah, it shows you have a better understanding about the algorithm stuff. Yeah, awesome. That's it. Hope it helps. See you next time. Bye bye.